to Physics 2212 Lab 2, which is brought to you by yours truly, Jake Bernstein. Here's a brief overview of what we'll touch upon in this lab. I'll provide an introduction, experimental results, computational model, and finish it off with a discussion and conclusion. Now, Lab 2 is super similar to Lab 1 with one key difference, which is instead of modeling the charge tape as single point charges, we're going to model the tapes as objects with evenly distributed charge across their length. And a preview of the result is that while the two models produce similar data sets, Lab 2 is likely more accurate, and both models corroborate key physics principles. What are these principles, you might ask? So the first one is Coulomb's law, and we all should be familiar with Coulomb's law in that it states objects with the same electrical charge will repel and vice versa. However, since Coulomb's law only applies to point charges, we have to extrapolate it and apply it over length to more accurately model the system. And then finally, any system on Earth is susceptible to the effects of gravity, so we have to include that in our calculations, which are seen on screen. The gravitational force is modeled there, F equals mg, and Newton's law states that since the system is in equilibrium, the force of gravity is equal to the electric force. And we can capitalize this on and use it to calculate the charge on one piece of tape, Q, using the formula above. And I chose not to derive it. It's well within the scope of the class, but this formula is on the formula sheet, so we are able to use it. Here's an overview of the setup. Our system is the two charged pieces of tape surrounding our earth, blocks, and table. And first we prepared the tape, then charged it, then mounted it as seen. And then we record the measurements, which allow us to conduct this lab. Now, I wanted to highlight two key figures as derived in Lab 1, one being the force of gravity, which is pictured on screen, and the second being the charge. We'll revisit these when we compare the two models. Now we have our code. It's a little cut off, but you can see the constants in the top left. We had to derive those. And then right below it, we have code that will find the electric field. That's just kq over r squared in a three-dimensional body. And then below that, we have a definition that'll help us model the line as infinitesimal point charges that all contribute to the overall charge. And then to the right, it's a little small, but it's not as important nor mathematical, which is the creation of the actual tapes, the top tape and the bottom tape, and then our scale factors right below that. And then this is the big chunk of code, and from lines 108 to 128, you can see my nested for loops, which essentially calculate the individual charge contributions and then sums them. This is kind of the equivalent of an integral from one side of the tape to the other, but instead we use summation. And then 135 to 147 is for aesthetics and establishes the visual representation of the forces. Here, after all that code, is our results, with the magnitude of the electric force, green arrow, being super similar to the magnitude of the gravitational force, which is pointing down, yellow arrow. Then we have our comparison. Lab 1, you can see force of gravity is equal to the electric force, and then the charge on one piece of tape is 4.04 times 10 to the negative 9 coulombs. Lab 2, we have pretty similar figures within a margin of 1, I think that's 1/100,000th. And then our charge tape is 1.11 times 10 to the negative 8 coulombs, as calculated with the formula a few slides back. And then some key assumptions we used are that we had to assume each U-tape we made had about the same amount of charge and it was evenly distributed. And then we had to neglect the effects of air resistance and frictional force, which could contribute to this discrepancy between the two forces. And the bigger picture of all this is that Coulomb's law and associative properties were verified through our results. And although we can model the interactions of charged objects using the point particle model, the uniformly distributed charge along a rod is a little more effective in this system. Some possible errors are accidentally touching the piece of tape, transferring some electrons from my finger, imprecise measurements, and then uneven charge distribution throughout the piece of tape, which is pretty likely. Last but not least, we have our conclusion. The what if is up there, I won't read it, but as calculated in Lab 1, the charge on one piece of tape is pictured there, whereas the charge on one piece of tape is 1.11 times 10 to the negative 8 coulombs in the model used in Lab 2. And the key difference is that Lab 1 treats the system as a point charge, whereas Lab 2 addresses it as uniformly distributed charge along its length. And these estimates differ empirically, because obviously two different formula were used to derive the charges, but logically, the model in which the tape is modeled as a charge rod factors into account the infinitesimal contributions of force by each section on the length of the tape, rather than just treating the tape as one single point charge. And because of this, the model used in Lab 2 is slightly more effective and is more likely to be closer to the real value. Thanks a ton for following along. I hope you have a great rest of your day.